Fitch system for first-order logic, or first-order Fitch, is similar to that for Heilbronn logic. We have the same logical rules and the same rules for quantifiers. There are some new rules to handle equations, and some rules we must discard, namely domain closure and induction. In the Fitch system for first-order logic, we include all 10 of the rules of inference for propositional logic and the 10 logical rules for Heilbronn logic. We have negation introduction and negation elimination, implication introduction and implication elimination, biconditional introduction and biconditional elimination, and we have introduction and elimination rules for conjunctions and disjunctions. We also include the 4 rules of inference for quantifiers from Heilbronn logic. We have universal introduction and universal elimination, and we have existential introduction and existential elimination. Our first new rule of inference, the rule for equality, is called equality introduction, QI. According to this rule, we can write down any equation in which the first term and the second term are identical. For example, without any premises whatsoever, we can write down equations like A equals A, f of A equals f of A, and f of x equals f of x. Our second equality rule is equality elimination, or QE. Equality elimination tells us that when we have an equation and a sentence containing one or more occurrences of one of the terms in the equation, then we can deduce a version of the sentence in which that term has been replaced by the other term in the equation. In order to avoid unintended capture of variables, QE requires that the replacement must be substitutable for the term being replaced in the sentence. It's the same substitutability condition that adorns the universal elimination rule of inference. Note that the equation in the equality elimination rule can be used in either direction. That is, an occurrence of tau 1 can be replaced by tau 2, or an occurrence of tau 2 can be replaced by tau 1. For example, if we have the equation x equals b and the sentence hates of xx, we can infer hates of xb, we can infer hates of bx, or we can even infer hates of bb. And that's it for equality. To finish off the proof system, we need to deal with domain closure and induction. While these rules are sound for Heilbronn logic, they are not sound for first-order logic. Simply guaranteeing that a sentence phi is true of every ground term does not necessarily mean that it is true of everything in the universe of discourse. Hence, these rules no longer work. The fix is simple. We just drop the 2 rules. No domain closure and no induction of any sort. Okay, that's it. To summarize, Fitch for first-order logic is similar to Fitch for Heilbronn logic in that we include our logical rules of inference and our rules for quantifiers. There are just these 2 differences. We include 2 new rules for equality, and we eliminate our domain closure and induction rules. Okay, now let's see what we can say about this proof procedure. Remember that a proof system is sound if and only if every provable conclusion is logically entailed. In other words, if we can prove a sentence from a set of premises, then the set of premises logically entails the conclusion. And a proof system is complete if and only if every logical conclusion is provable. In other words, if a set of premises logically entails the conclusion, we can prove it. The nice feature of first-order logic is that the Fitch system is sound and complete for first-order logic. Logical entailment and provability are identical. An arbitrary set of sentences delta logically entails an arbitrary sentence phi if and only if phi is provable from delta using the Fitch system. By contrast, the Fitch system for Heilbronn logic is not complete. However, this does not mean it's not powerful. In fact, the Fitch system for Heilbronn logic is at least as powerful as the Fitch system for first-order logic. Given a set of equality-free premises and an equality-free conclusion, we know that if the conclusion can be proved from the premises in first-order logic, then it can also be proved from the premises in Heilbronn logic. Moreover, the result holds in general when equality is replaced by an equality-like relation, such as the same relation that we saw in some of our examples. The fact that first-order Fitch is complete does not mean that it's more powerful than Heilbronn Fitch. It's simply a result of the fact that first-order logic is not as strong as Heilbronn logic.